say these chalks are great. so let me start. Okay, so I'm going to discuss some topics related to dynamics and moduli space of curves. And curves here are complex curves or hyperbolic surfaces. But so whenever I talk about some results that I've done is joined with mostly with Alex Eskin and Amadi, but I'm not going to discuss only our results, so it will be long before I even prove a theorem or state a theorem. So maybe I'll start from, okay, so the discussion is about, so there's certain natural flows that I want to motivate defining these flows, define over some bundles. I won't use this much, over mg, which is the moduli space of, say, hyperbolic surfaces, or if you prefer, complex curves of genus G. So somehow the topology is fixed, and there you have different structures on the surface. Maybe it's a hyperbolic structure, complete hyperbolic structure on this compact surface of a finite volume, or this compact is finite, or you have a complex structure, and you have the moduli space of all possible complex structures that you can put on a surface of genus G. And then we want to find, we will see how basically deforming the complex structure, or actually the bundle here is essential. Changing the structure and seeing what happens to the structure can help you get results about properties of a given hyperbolic surface, or in this case, mostly it would be a complex curve plus some additional structure. Before I even, before I define anything or say what I mean, what the flow is, how we define it, what I mean by dynamics over this, maybe I want to discuss a few problems, a few questions, just to motivate the work that I'll be discussing. And so if you have heard any talks about anything related to these topics, the first example is usually billiards and the trajectory of a ball in the billiard table, but I don't want to start from billiards, so I'll keep the billiards for the last, as a last example, but we'll get there. So I'll start from a purely combinatorial question, which, I mean, even though it's a combinatorial question, it's certainly related to surfaces. That's why I'm mentioning it, topology of surfaces. Which starts from basically, you start from with an interval and you divide it into n pieces. Here I'm dividing into 4 pieces. And one side of the interval you put, I mean, there are different versions of this. You put, so this small n is fixed, but you put capital N semicircles with all the same center, for example. This doesn't have any respect for this. There's nothing about this interval. And the other side, on each, so if I did it, well, I mean, on each interval, I'll have an even number of, so then I will have A1, A2, A3 to AN, and I just put, so somehow n capital N is fixed, and A1, you can imagine A1 to AN are somehow random integer points with the sum is equal to n. And one side of this interval I'm putting for AI, I put A1, I put A1 semicircles. For A2, I put A2 semicircles with the all centered at the center of the interval, and A2 and AN. So So this way, given A1 to AN, with sum is equal to n, I get a shape of, so it's now I had my half circles here, and I added this half circles, which depended on A1 to AN. But that basically, A1 to AN determines a shape like this. And the question is, what is the probability? So you can start and go around. Either, I mean, at some point you will come back to the same place, but it could cover the whole thing, or this could be just a connected cycle. Of getting a connected cycle. Or two of them, or as n goes to infinity. Sorry, n it goes to infinity, and sigma I is equal to n is somehow a random point in the random point where AIs are integers. So okay, so this is a little yeah. So you can certainly generalize this kind of questions very easily into. We play with this a little bit. You'll see that you can very easily make this into a question about. There's nothing about the semicircles or the way we define this. We can start from a graph, and maybe I can. I mean, you can see even the interval in this. You can start from a graph, and you can have n incoming edges and n outgoing edges. And then you have this here. You can have a permutation. To join the incoming and outgoing edges. And each, say, if you want to make the problem easier, each incoming edge will go to, maybe I have 1, 2, 3, 4. Maybe 1 goes to 4, 2 goes to 3. And of course, I can't draw it on the plane, but it's OK. I look at it as a graph. 3 goes to 2, and 1 goes to 4. So, OK, it's just a graph. And then if you assign A1, A2, A3, A4, where the sum of AI is equal to large capital N, you can basically do the same thing that we were doing here, meaning that I can just put something very similar to that without using circles. I can just use these integer points, AIs, to draw parallel lines. So if I have 1, and therefore I'm looking at the number A1, I'm putting A1 lines parallel to the first one. And then I'm putting A2 lines, not even parallel, but A3, A4 here. And here I'm putting, again, A1, if A2, whatever these numbers are. And I'm just connecting. And here, I'm just using, I have now, because the sum is capital N, I have capital N strands here and capital N strands here, which are joined 2 different ways. So one way is just this here. It's just without any self-intersections. And the other way is through the lines of the graph. So A1 to AN will determine a loop. And the question is, when is this loop connected? Or what is the probability of, to be more precise, probability of getting a connected loop as basically n goes to infinity. So maybe this you choose from A1 to AN integers uniformly by restricting that the sum is less than or equal to n. That's the probability of getting it. It's sort of hard to get something connected. And if you want to see what it means, you can put some conditions on these integers to see when it's connected and it's not. And to get a sense of this, you can do it with the simplest possible graph with 2 this goes here, and this goes here. And if I put A1, A2, and A1, A2 here, sorry, and A1, A2 here, sorry. What I'm getting, so what I'm getting here is that, so the loop is connected if and only if A1 and A2 are co-prime. So you get asymptotically, as n goes to infinity, you get something about the probability of getting a connected arc, which is non-zero, which is the probability is 6 over pi squared, which you can calculate using elementary number theory. But as you have more and more intervals and your graph is more probably complicated, then you can't use anything. You can't say if this is connected or if it has two connected components, if and only if you can't easily write it in terms of some conditions in terms of AIs. And yeah, but as you can see, this is, of course, secretly, there's a surface behind this question. And the surface is the surface that you get by thickening the graph, which is we start with, it's a ribbon graph, and gluing basically disks to get a compact surface. So for example, if I do this 1, 2, 3, 4, 1, 2, 3, 4, and this kind of thing it's related to the interval exchange math. Is something that people study a lot and they have nice properties. But if you do it, for example, and if you thicken the graph, this 1, 2, 3, 4 that I have there, and basically glue back a disk to make it a compact surface, you get a surface of genus 2. So for this permutation that I have, or as I'm sure most of you have seen, if you do this kind of graph and you thicken it, you get a surface of genus 1. So these are questions related to some topological properties of things on surfaces. And so here's so this is, the third question is basically what a generalization of this, that you can start from a surface of genus G. And so you're looking at different maybe patterns on SG. And a pattern, I mean, it could be maybe so up to now, so this SG is a surface of genus G, and here I'm only interested in the topology of it. There's no geometry on it. And it could be a union of homotopic classes of closed curves. So for example, you can have this guy, this guy, this guy, I don't know, this guy, and maybe some self-intersection in the between. So this would be your gamma, and then you want to see basically, whenever you can draw one picture like this, and even if these gamma i's are up to homotopy, you have a very natural action of a very important group on the set of patterns of this type on the surface, and the action is by the mapping class group of G, which is the group of, say, diffeomorphisms or homeomorphisms here, orientation, preserving, or homeo up to isotopy acts on the set of patterns of this type. So all I'm saying is that if you have a very complicated homeomorphism, and I give you this picture, you can look at the image of this picture on the diffeomorphism. It preserves the type, the shape of this, and just makes it look, the lengths would be longer, but in fact, they're not more complicated. If whatever like self-intersection or whatever properties these have, the new pattern will have the same properties. For example, if you have one simple curve, it will be always simple. If like 10 of them intersect, and it's whatever way. It's basically the same thing topologically. You get the same thing if you cut the surface along the edges of this pattern. So, and then, but okay, so you have all the patterns of this type, which I write as mod G dot gamma topologically. And now I wanted, so if you want to try to understand, say, a hyperbolic surface, I think hyperbolic surfaces are just hyperbolic, easier hyperbolic surface or hyperbolic structure here. Or maybe you have a negatively curved distance function or metric, or just something which is not positive, the curvature. You can basically look at the statistics of, so you can order your gammas. So these are, so an element of a mapping class group is just, you can think about it as a diffeomorphism up to isotopy. And you can look at the set of, order the set of G gammas, and then measure this, somehow the complexity of G gamma just by, if I give you a union of closed curves on a surface, you can do it by one way, if you have something which has negative curvature, by basically the length. This is, so each, because if you have something which has negative curvature, every closed curve has a representative which has the minimum possible length, and that's the length of that curve. So that's a unique geodesic representing that, and then you write this as whatever, if this is gamma tilde, L gamma tilde of X, where gamma tilde is a pattern of type gamma. And the type of questions are, first of all, maybe the growth of the lengths, or depending how it depends on X, or even more complicated somehow is how if you have, for example, two curves, alpha 1, alpha 2, in gamma is the statistics of the ratios of lengths. As the length of lengths of subsets, as the length of the big guy, which is the union of all of them, tends to infinity. So, and because I won't have time to discuss these problems in details and how you do them, I will just say here, for example, no matter what the complicated shape that you have, gamma tilde, is you always get something. And I want to compare this with another result that I will mention. So the number of gamma tilde is of type gamma of length less than or equal to L, grows like L to the, okay, if you have the genus, L to the 6G minus 6. So it can be anything you want. But of course, there are many closed curves on the surface there. I mean, for those of you who know that if the length grows, there are exponentially many closed curves on a surface of length less than or equal to L. But the point is that they become more and more complicated in terms of the pattern. And in fact, if the length is L, you will likely have square root L self-intersection. So there's no way to get things about all. This is not about all curves. The same way as I should mention, this is not about all these kind of meanders that if you have seen it in, I don't know, even statistical physics. This is about the ones with, like, of bounded type in some sense. And the same way, these are about getting estimates about the guys of bounded type. No, the topology is not getting more complicated as the length grows. So it's a little bit different from looking at all possible curves. Okay, no, finally, so these are things about surfaces. That is, you have like, so the first two are basically combinatorial and or topological, and the third one is like fixing. You have a fixed hyperbolic structure, and you want to see sub-patterns in terms of the length, the statistics of the ratios, and see if you can distinguish different hyperbolic structures based on that or not. OK, so finally, so these are the problems motivating this. So the finally get the billiards. So the type of, there's several questions which are related to the dynamics over moduli space, and it's hard to say much about them without using the moduli space. And that, I mean, these are about the behavior of, so the general problem is trying to understand the behavior of the trajectory of a ball in a billiard table. But this is a very this is very difficult, and your table maybe if you don't put any conditions on it, could be anything. And this is of course a very difficult problem. There are lots of results that I won't have time to discuss. But so you have a point, and you hit the ball at this point, and then it goes and it bounces off, and the point, and it's in a billiard table, meaning that these angles are the same whenever you intersect the boundary. And you want to see what happens to the to this point. And are there closed orbits? Are there dense orbits? Are the dense orbits spending a fair amount of time in all subsets of the billiard? So there are many problems like this. But maybe instead of the billiard thing, first of all, we instead of having a smooth thing, we can also look at even at the polygon billiard. And then whenever the ball goes to one of the, so basically the conditions are the same. The only difference is that whenever the ball goes to one of the vertices, it disappears. So you don't continue. So there are many finite trajectories. There is no way to continue, but whenever it hits the boundary, the angle, this angle and when it reflects, the other angle, they are the same. So another problem which is related to this is maybe I want to mention two other problems and then discuss the relations with the dynamics. It's called illumination and security problems on billiards. OK, so there's one question, which is, again, these are quite old questions, that if you have a room and the walls are made of glass and you have one light source somewhere, does it necessarily make the whole room bright? Or so is it, of course, if it's a convex set, it does. So you have a billiard. The problem is that it might not be convex. What can you say? And then you have a point. And you're allowing, so light means that, of course, there are variations of this question, but light means that you're looking at all the rays coming out of one single point, and you allow them to move forever. So it goes, and then it goes, intersects this, then it goes, intersects this. Of course, then it goes, maybe at some point comes to this corner, maybe not. But then there you have all the possible, given P, so given P, you look at all rays starting from P, and you are interested in the possible set of, are there points not covered by this one source light? Or what can you say about the set of points which are not covered? And in general, I mean, there are examples of actually billiards which are not illuminated at one point. But not much. But it's very hard to say what the set that can't be covered consists of. For example, in many cases, when the billiard, and I'll discuss this a little bit more, when the billiard is slightly nice from our point of view, then the set of points which are not covered like end up being finite or at most countable. And OK, so but maybe before I mention these kind of results, I will say, so this is one problem. Another problem is that maybe you have a source and another point Q, and maybe there are many ways of, there could be infinite, I mean, there are infinitely many ways of getting from P to Q, maybe, but you want to see not only if it can get from P to Q, but can you block it? Can you block P, Q? So by this, I mean all geodesics from P to Q in the billiard. And whenever you go to this, one of the vertices, it disappears by finitely many points. This is a. So if that can happen for all P and Q, say the polygon is secure. So for example, so because maybe you don't want the thing from P to reach Q. There are examples of the security guards, and if you have a president and the terrorist, and that, I mean, there's all sorts of interpretation. But you want to have finitely many blocks so that any geodesic ray from P to Q by this procedure will go through one of these finitely many points. So you can imagine these are hard problems. And one, maybe this looks very, that's quite unlikely, but the torus or square is secure. And of course, you can do this even on manifolds. Like if you have a manifold, you have 2 points. You want to block all the geodesics going from one point to another by finitely many points. Is it possible that for any 2 points, there are finitely many points that any geodesic between these 2 points will go through one of these finitely many points? So conjecture is that there's a lot of actually work on this area. Maybe I'll just refer to Hodkin as a reference. And the conjecture is that, so a manifold at least, a Riemannian manifold, and I'm not sure if, I mean, I'm not convinced that it's true, is secure if and only if it's flat. And I think it's known that if it's flat, then it's secure, and there are lots of examples where this happens, that if it's secure, then it's flat. But in our setting, I mean, this is a simple little exercise you can do that. Any 2 points, there are lots of, if you look at all the geodesics in this billiard from any given 2 points, then there are finitely many points, and you can imagine these are basically the middle of this guy, and then you can draw some other finitely many geodesics, and the middle guys will be the middle of all the geodesics between these 2 points. A simple exercise that you can do. But OK, so maybe by geodesic, I mean rays. It's a flat. Here, so it's a more general thing about geodesics if you have a Riemannian metric. But here, geodesic means that with respect to the flat structure with R. So there are lines. Of course, this is one, but there are more complicated ones because something can go hit the boundary several times, right? And then end up at the other point. these 2 points are fixed. These 2 points are fixed. And the question is if you can find finitely many points so that any way you go from this point to this point, you go through one of the finitely many points. And this is, yeah, this one is very simple to find. But, OK, so the, no, OK. So I mentioned these problems, the illumination security problems, and the properties of trajectories of billiards because they are closely related to surfaces. So in a case, so that we are interested in the case where all angles are rational multiples of pi. The reason is that otherwise we can't say anything. So in general, in general, all these problems are very difficult, but it's even an open problem if you can always find a closed orbit in a polygon billiard, or even there are interesting partial results, but even I think in a triangle, there are results by Rick Schwartz. A lot of things are known, but in general, it's not even clear if there is one single. So what is a closed orbit? Closed orbit as you start and you go, but after finitely many times, maybe not the first round, but okay, after some time, oh, okay, okay, maybe even you come back like this, or after some time you go around more and more, and you come back this angle. So it's a closed orbit. So it's a periodic trajectory. So closed orbit would be a periodic trajectory. So these are. So you can't say anything if you have an arbitrary polygon, basically, or it's very hard to get even partial results. But the conjecture, or what happens in, maybe I should say first, so what happens if P is a rational polygon? You do get many of them, and not only that, you get, so given L, you get roughly L squared closed or periodic orbits, so family of periodic orbits of length less than or equal to L, which is different from what we had there. Interestingly, it doesn't depend on how many edges your billiard has, and I wrote family here because also in the case of a square, you can see this is one closed orbit because it goes and bounces and it comes back. But this is another one. So they come in families. So once you have one closed orbit, if you move it parallel to itself a little bit, you go around, it's another closed orbit. So it's not about the number of them. So when two of them are in the same family in this way, we say that they are the same. So you have L square of them of length less than or equal to L. And this is, but so there are some bounds by Vorobets to refer to, but this is due to Maser and Eskin, the asymptotics. And it does use a lot of the things about properties of the dynamics of the actions that we are going to discuss on the moduli space. So even for that, it's not like you look at the billiard and you see where these things are. And the conjecture, I think, by Katak is that for an arbitrary polygon, as L gets big, you have L squared, roughly, of closed orbits of length less than or equal to L. But we can't even find one. So I'm not sure where the conjecture is. I mean, maybe it's just based on analogy with this. And it's very delicate because, I mean, you can see, or maybe you can approximate the billiard with rational billiards, but these things are not, these questions are not somehow stable. You lose a lot of information by approximating your billiard. And to bombard you with a little bit more, a few more questions. So given, again, if you have a, I mean, that's a question for general billiard, but you can also ask the types of trajectories. For example, there are some closed, hopefully, I mean, if the conjecture is right, maybe there are closed, meaning periodic orbits for a trajectory of a billiard, but you want to know if there are dense ones, or are there ones which are not closed, not dense, and even if you know that, so here's a, even if you know that things are either dense or closed, the question is, can you find nice billiards such that every orbit is either closed or it gets, okay, so equidistributed, which is a technical term for the trajectory that spans, like if you have an area alpha, basically it means that if you look at the long trajectory, it should spend alpha over the area of the billiard percentage of its time in that open set. So it's doing this the fair way. It's closed, or when it's dense, it becomes equidistributed. And actually, so that's, I think, so there are examples of such n-gons, basically regular n-gons, which were discussed by Veach, who realized that these regular n-gons are optimal in the sense, and they are very nice. But there are examples of, so it's, maybe I should here, that's very hard to even in the case that the angles are rational multiples of pi, to prove that some billiards are optimal or not. And so for but there are things that we know, but I think mostly from the case of so-called L-shaped billiards, which is done by Kurt. Basically, you can see when it's optimal, and if it's basically if every orbit is either closed or dense, then the orbits are closed or they become equidistributed. So there's a lot of things we know, but unfortunately, that's, I think, these are the type of billiards that will give you surfaces of genus 2. And after that, it becomes much more complicated to study these things. OK. And I should say maybe a little bit about this. About the illumination problem. So there are, in the case of, again, for general billiards, it's much more difficult, but the case that the billiard is rational, all the angles of multiples of pi, so there are results by different people, and and also by, I think, another group of people, Montelli and Weiss, but they're all showing that in some cases, or their work for all rational billiards, if you have this one source, this set of points, you basically cover most of the point on this rational billiard. That is, the set of points which are not covered are like countable or maybe finitely many points. OK, so these were the lists of the questions that I wanted to discuss. So maybe I will say a little bit about how these are related to dynamics of modular space of curves, and state some results. OK, so the reason that so these are all these problems can be done in an easier way, or there are ways of approaching these problems. The case where the polygon is a rational polygon is because of an old but very nice trick. Is called unfolding. And OK, I'm going to do it for the simplest case of a square that we have seen it, and you can imagine you can do it for general billiard with whose angles are rational multiples of pi. So the trick is that instead of looking at the reflection of the ball, when it hits the wall or the light, instead of that, you look at the reflection of your billiard with respect to one edge, and then glue it next to the original one. And instead of looking at the reflection, just continue the path. And so knowing things about this shape is the same as knowing things about the original billiard. And so the nice thing is that if you start from P and you take reflections with respect to edges, and then at some point you can, for example, if you have P, you have 4 of these guys. But then the number of guys that you get is finite, because I mean, this is just a simple exercise, because the angles are rational multiples of pi. After some time of doing this reflection, it comes back to itself or some multiple of 2 pi. So, but I mean, you can do the same thing if the angles are irrational multiples of pi, but then you get a very complicated space which has, like, I mean, very difficult to understand. But what happens is that if you have a rational billiard after gluing, so you get finitely many of these things, and you can, at the end of, once you do all these gluings, this will give you a surface, a compact surface. If you do it, for example, for a square, you get a torus. You get 4 of them, and you get a torus. And a straight line, and it's a compact surface, and it's a flat one. So meaning that straight lines make sense. So from P, so for example, you get this guy, but if you do it for a more complicated billiard, and you put these next to each other, and then the glue. The important thing is that all of this, you have to do it slightly maybe more carefully, but all of these, it's the reflection, sorry. You can use the gluing by, that will glue parallel lines of a polygon. So this is very similar to the case of like having a 2n-gon, and then which is regular, and glue the parallel edges of the polygon to get a surface. And Okay, so that's what you get. So you get a surface with basically which is flat, but it's not quite flat. I mean, the surface, if you do it this way, you get a surface of genus 2. So you can't expect this thing to be flat, even though it looks like a piece of R everywhere. But the point is that you have to be careful about when you do the gluing, you have to be careful about having the vertices having total angle 2 pi, which fails to happen, except for this nice case. You get a flat structure with finitely many singularities, where the sum of the so the angles at these points is more than 2 pi. It's 2 pi times an integer. Okay, so given a billiard P, you do get a flat surface. But this flat surface, I mean, has a lot of structure. And I just want you to think about the torus case, or maybe the simple case of this L-shaped billiard. So you have finitely many points. Everything else is basically coming from the flats of R2. And in fact, it comes with this structure, a complex structure C, because all you're doing is you are gluing parallel edges of some polygon. So it actually comes with a complex structure from C, and it has even more structure than that. So it's a complex structure of C, and you also have, because you are only, so the maps that you are using, so the gluing maps, depending on how you choose your polygon is, basically the gluing maps, if you are in the nice case, that are basically just moving things by a vector C. So not only the complex or plus minus, but for now we can ignore that. So the structure that you have, not only the complex structure is preserved, there's a one form dz on C, which is well defined. And this one form, I mean, it's well defined because it's well defined. It's the same if you dz plus C is equal to dz, even formally. So this defines, in fact, one form, a holomorphic one form. On a surface of genus G. G depends on the shape of the polygon. And so the main reason that this is useful for understanding, for example, the set of closed, so if the set of closed or periodic orbits or not, is that a lot of nice properties are preserved under a natural, and there is a natural action of SL2R on this space that I will just write it down, but before I do it, the SL2R is the group of, I mean, this 2 by 2 matrices determinant 1. And if you want to see how it acts on, SL2R doesn't act in an obvious way on the space of complex curves of genus 2, or at least we don't know. Yeah, I mean, there doesn't seem to be such a nice action. But if you have a holomorphic one form, say, which comes this way from gluing parallel edges of a polygon, SL2R does act on C, which is R2. So if you have this, you can just use whatever SL2, your element of SL2R does to the polygon, and you makes it to a different polygon. But the different polygon that in SL2R being parallel is preserved, so you can glue the same edges and get a different polygon. And one picture of this maybe, so this is one case you can do, but one picture of this would be maybe if you have a regular n-gon, and you are basically gluing the parallel edges of this, and you want to see what happens if you act by SL2R. You can act by SL2R maybe by the e to the t, 0, 0, e to the minus t as a matrix, and it becomes, one side becomes long, and the other sides also become long, but basically it becomes thin and long. But parallel edges are parallel, so you can still glue the parallel edges. And get another structure on a surface, and you can do this here. So maybe to fix some notation, so I want to look at the space of the one forms, holomorphic one forms, on a surface of genus G. And this A1 and AK, it doesn't matter. I mean, they are very important, but they are basically just keeping the singularity type, fixing A1 to AK. And what I try to discuss here is that, so first of all, there's a natural SL2R action on this space. And there's also, if you have this kind of flat structure, there's a notion of, if you have a complex structure, it has a volume form, which comes from the canonical volume form on R2. So if you multiply your holomorphic one form by 10, the area is multiplied by 100. So that's it's natural to look at the guys with one forms area 1 with this, and SL2R, because it's area preserving, it preserves this. And this is and the reason that we have this A1 to AK here, of course, if you have any holomorphic one form, you can act by SL2R, but the singularity type, which means the angle at the total angle at this kind of special bad points, the singular points, is going to be preserved on the action of SL2R. Everything is preserved. All the natural basic things are preserved under this action of SL2R, the topological things. So it makes sense, instead of looking at all of them, to stratify them and look at the set of guys with given singularity types, and hope that this is kind of a connected space in terms of this SL2R action. And in fact, there are, I mean, but still you have to, even if you add this data of A1 to AK, this space is a very mysterious space as a topological space. So you're fixing the singularity type, and you're looking at all holomorphic one forms of that type, and so there are results about when this thing is connected. Most of the time, it's connected. Most cases, except for some hyperelliptic issues, but so there are some results old by Zurich and Kontsevich, and others about when these are connected and what can you say about the connected components of them. But the topology, so I want to emphasize that the topology of this this H1 to AK is very mysterious. As we don't know, I think there's a conjecture that says that this space is a K pi 1, but that's not known. Basically, not much is known about this. And the tricky thing about the space is that this is certainly, for example, not compact in any way. And there are several problems with this kind of space. One is that the surface itself can degenerate. The space of modular space of curves is not compact. But also the singularities can get close and collapse. And if you fix the type of singularities, collapsing singularities is not allowed. So so that's the other problem. But so the topology is not easy to understand, but sorry, when did I start? Okay, so okay, so maybe I'll finish. Maybe I'll just state one result and then I'll continue next time. Okay, so here's the here's this space H1 A1 to AK, and we have a natural SL2R action here. And I should also say, so this is a bundle. I mean, it's not a bundle, but there's a projection map into the moduli space of, if the genus of this thing is G, the moduli space of curves of genus G or hyperbolic surfaces of genus G, just by forgetting about this one form. And this is but again, this projection map is also very mysterious, and we don't understand it so well. So so it's a little bit hard to say, to translate the results on this to results on MG. Because, I mean, if I give you a complex curve, there's no way to deform it, but this omega at least gives you a way of, if I give you a complex curve plus a holomorphic one form, there are ways of deforming it by using this action of SL2R, but then getting back to MG is in general quite difficult. So, so the general problem here is so understanding this action properties of SL2R on, in general, A1 AK. So, for example, you can ask, dense orbits, are there dense orbits? So what are the closed orbits? So the type of questions that we asked. And these basic questions are basically, I mean, there's a lot known about these spaces based on results of generic properties based on results of Maser and Veach. It goes back to Maser and Veach about that there exists a measure, maybe I'll discuss this a little bit next time, measure on H, which is in the Lebesgue measure class that I haven't told you about, which is invariant under this SL2R, and the action is ergodic. But for now, what it means is that basically almost every point has, with respect to this measure, has dense orbits. And what I want to discuss next time is trying to say what every single orbit would look like. and discuss some of the related results. But maybe I should say here that, for example, knowing every orbit would help you to understand, for example, if one single x omega has a periodic orbit, but this means now on the polygon, having a periodic orbit is preserved by the action of SL2R. In fact, the nice thing about the action of SL2R is that it sends, if you have a holomorphic one form, which is basically coming from gluing parallel edges of a polygon, if you have a closed loop and closed periodic orbit on one, and you act by SL2, you get another closed loop, because basically this SL2R will send straight lines to straight lines on your surface 2. So periodic orbits will go to periodic orbits. Unfortunately, the length is changed, but it acts on the holonomies in an equivariant way. So if you want to find a closed orbit here, you can act by SL2R and try to reach some region. So try to reach a point where you know there are periodic points. And this will give you a periodic point in the original thing. So, but of course, this is, and then having a closed loop is some open set also in H1, H1 to AK. So it's basically, you want to move this by SL2R and get to some place that you know you have periodic orbit. So actually, the proof of this, that you have always a periodic orbit, it's not quite along these lines to using any kind of classification, but it's somehow it's easier to use SL2 to, for example, degenerate the surface, almost degenerate the surface, and then prove things by induction close to the boundary and pull it back. But basically, having this SL2R action helps. It's a big crucial point for getting periodic points. OK, so maybe I'll even state the theorem next time, because I have time.